Linear combinations and transform bases, the hidden beauty in simultaneously diagonalized degenerate matrices. In problem A24, we want to show that alpha tilde, so the transpose or some new vector, computed from equations A88 and A90 are eigenvectors of V. And here are some equations that we're going to need for this to happen. This is the middle of 87, so 87.5. Here's 88, that's mentioned in the question, and here's 90. And for context here, since this question doesn't give much of it, this is dealing with simultaneously diagonalizable matrices with a degenerate spectra, meaning that we have repeated eigenvalues. And here, C represents the linear combinations of the eigenvectors themselves, which is represented here, meaning that, if we have two matrices that commute, right, say T and V is what they use in the book, and we know that we have some eigenvalues of T, which then give us the eigenvectors, then we could say that they are also eigenvectors of V, and that's what we're trying to show. So that's why we're writing them as a linear combination, because if they're a linear combo, they could still be in the eigenspace and we're fine. And then this tells us, well, some other things go on in the book. And to recast this as a transform bases, since we know that if I have two commuting matrices, they still commute regardless of basis. That's what we showed last question in A23. So if we reframe the question, then we're left with a new eigenvalue equation to solve in terms of the old vectors and what we see here, d1i, d2i, and d1i, d2i here, with the original linear combination coefficients given here, and some new eigenvalue or some scalar multiple. So with that kind of landscape, roughly sketched out, although you would want to read the book for the full context, all we're trying to do is show that this recasted eigenvector image is looked at as an actual eigenvector, and we're going to have to verify that by making sure that we're a scaled multiple. So again, to ensure that this is an eigenvector, again, we want it A tilde or alpha tilde in this write-up. We need to ensure that it is a multiple of the current eigenvector. As such, from equation A90, we have this eigenvalue system. Okay, so if we do the multiplication here, row to column, row to column, row to column 1, row to column 1, second row to column 1, and then we distribute that Vn here. We see we just get two equations, again linear. And so setting up for two cases, since we have two eigenvectors to test for, this is for the eigenvector 1, highlight it with the yellow 1. This is for eigenvector 2, highlight it with the yellow 2. So the idea here is that given that we have some new eigenvector for 1, right, and we see that this is equal to d1, 𝐿11a1 of the original eigenvectors, plus d2a2 from the original eigenvectors from equation 88, we can go ahead and use this linear combination in the, this one specifically, in the eigendecomposition and show it's just another linear combo that leads to a scaled multiple. So to facilitate this, we go ahead, distribute this V into both of those, since V is the matrix or the transformation. We see that the V acts on the vector itself. Since D1 is just a scalar, we can factor it out. D21 is a scalar, factor it out. So V acts on alpha 1, alpha 2, as you see blue and green. So after doing that, then we see clearly that by highlighting the action of V on the alpha vectors, we get that this V acting on alpha was just a linear combination of the other two vectors. So again, in the book, they talk about the necessity for certain components of these two vectors, the off-diagonal terms of C to be 0 and vanish, blah, 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 hence the reformulation of this. So then we go here, we have 𝑑21 acting on this definition here, which is just another linear combination. And then what we see here is that in doing so, we end up with this distributed form. Now we're going to collect the terms from alpha, collect the terms from alpha1 and alpha2, upon which we see that it looks like another distribution of numbers here and here on both the alphas. So what we're going to do is we see how it's D11, C11. We're going to switch those over thanks to the commutativity of normal numbers. Switch that over. And we see that that corresponds to this component of the matrix equation. So that gives us this component here. Let's see that in action. So continuing on, we go ahead, switch out all the component-wise multiplications. Since we can do that, they are commutative. And then we see from that second line, first matrix result, we get V1, D11, V1, D21, acting on the vectors respectively. We'll go ahead and distribute it, so get rid of the curly brackets. From here, we'll go ahead and rearrange. Factor out the V1 from both terms. That leaves us with D11 alpha 1, D21 alpha 2, which gives us back the original vector definition with some scale factor. So since it's just a singular scale factor, we're good to go, and we satisfy the requirements for eigenvalue or eigenvector with this eigenvalue. And then if we recast this and do the same thing for alpha tilde 2, put it in here, go ahead, distribute and recast or redo the associativity of multiplication here. Once we factor out the scalars, plug in the matrix elements associated with them, then we're good to go from the original equation, 88. Then from there, distribute out. Now we're good to go. Collect the like terms, alpha 1, alpha 2, respectively. Then we see that we just go ahead and switch the elements already. Now we see that we're primed to use the matrix, the second matrix in that second row from last page. From there, we see that we can distribute these in, or substitute in rather, and then from this we can pull out the V2. Now we see that we're recasted into the same light of what we started with. As a result, we can put in the original shifted vector. So what we're saying is that V acting on the shifted or transformed vector 2 gives us a scale factor of the same vector, so we are an eigenvector, and we're good to go. Quick problem, one that's kind of messy, but utilizes things that we had seen previously thanks to the transformation bases remaining, where we had commutativity remaining unchanged. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. With this new playlist coming together pretty fast, I'm probably going to jump into the world of classical mechanics or statistical mechanics. Right now, they're running a poll between the patrons and a couple other groups that I have that are supporting this channel. See what it is they actually want to cover. So right now it's about 60% classical, 40% statistical mechanics. So we'll see what happens. Either way, we're going to learn a lot this new year, so I'm excited. And that being said, got to thank everybody who supported the channel thus far. And if you're interested in supporting the channel, please consider joining the Patreon community. The link is in the description below. And, welcome to the journey of physics and learning. Clearly, there's a lot out there. And with the AI revolution coming, or even started last year, universities are having to switch up how they're going about their teaching techniques. So now would be a really good time to be really self-interested in self-education and exploring topics and ideas that maybe weren't accessible previously. So definitely a broad vision coming ahead in 2025. So let's get ready for some fun. As always, thank you for watching, and until next time, stay curious.